Thank you, Rebecca. Hello, everyone. Thank you for coming to my 4-year review seminar. Today, I'm going to briefly introduce progress in my teaching and research programs. I will focus on one research topic, applications of agriculture system modeling in climate-smart agriculture. As I'm talking to the audience with diverse background and expertise, better for me to start introduce my own research background. I was hired in 2015 with my unique background, agroclimatology and agroecosystem modeling. Agroclimatology is a field in interdisciplinary science of meteorology, apply climatology disciplinaries for agroecosystems. The oranges related to the key role of climate change in plant and animal production. Agroecosystem modeling covers diverse topics. So what's modeling? Don't think it's far from you. We are using modeling anywhere, anytime in our daily life and our research activities. AI, artificial intelligence, gonna be the dominant role in our future life. That's kind of mathematical modeling. A simple equation describes photosynthesis or respiration. That's also modeling. Or you statistically calculate the relationship between tobacco biomass and precipitation. That's also modeling. We call that empirical modeling. Agroecosystem modeling belongs to ecosystem modeling, whose based on ecosystem ecology. It integrates biological and physical disciplinaries, provides the basis for the whole Earth system sciences. It uses concepts developed at finer levels that help us to build an understanding of mechanism for the whole Earth system. So you can see agroecosystem modeling works at multiple scales, addresses multiple processes. The mission of my job position is to use agroecosystem modeling and multiple data sources to systematically investigate impacts of climate change and land use on agroecosystems and synthesize agroecosystem knowledges for sustainable and resilient agricultural practices now and for future. As I know, it's going to be increasing need for such positions, not only our UK, UC Davis, University of Maryland, Cornell University, Iowa State University. Agricultural colleges already hired people in such position. Why we need such position? That's because we already recognize the most important thing of agriculture. Sustainable agriculture plays a dominant role in under climate change. Over the past decades, we have seen that huge impacts of climate change and extreme weather conditions threatening our food security system. At the same time, multiple evidence show that agriculture-related activities caused a lot of environmental problems. Increasing greenhouse gas emissions contributed to global warming a lot. No wonder. Climate-smart agriculture was advocated by FAO 10 years ago. It is an integrated approach to pursue multi-benefits among agriculture, climate, and other goals. All of us working together achieve the same goal. Since we are using diverse approaches, we have different perspectives. Let's look at the figure. The photo, what do you see? Dave may see the beautiful world of roots and consider, global warming, nutrient influx, root development, water and use efficiency. I think, let's see. Mark, you may care about our microbial activities influenced by global warming. And Ola may care about, soil moisture, deep soil moisture. Monsi care about phenology, integration with irrigation, how to enhance food production. Steve and Ptolemy care about, how to improve tolerance, drought tolerance in plants through selections in breeding. For me, I really care about the relationship between agroecosystems and environment conditions, land, air, and water at multiple scales. I'm pretty sure most of you are familiar with, certain scales. From field scale to land scale regarding climate, regarding, agriculture practices. You can see that at different scales, the related scientific questions to be resolved are different. For climate smart agriculture studies, we are working on diverse, different scales and related questions may scaling up from a molecular level to global level. We have seen a lot of field and plot studies conducted to study, climate smart agriculture practices. Widely adopt no-till, cover crop, biochar. That's in certain climate and soil conditions. But we are lack of deep understanding how the big, broad impacts of such practice at a larger scale. We are also lack of understanding the feedbacks of CSA practice to climate system. That's why I really care about climate change, climate smart agriculture. We focus on some indicators like crop yield, carbon sequestration, greenhouse gas emissions, nutrient leaching. Because the CSA purchase multi-benefit among food production and environment consequences, different goals. All these indicators related to food security, climate change, and water quality issues. That's what we care about, footprint, key indicators in our research programs. Driven by the scientific question over past 4 years, I created agroecosystem and ecological modeling lab and form up our team up. The overall goal of our lab is to study climate change, climate smart agriculture responses and feedbacks. There are 3 objectives. First, we'll improve agroecosystem modeling, help us understand, assess, and predict the impacts of climate smart agriculture practices. We have to incorporate such mechanisms into current agroecosystem modeling framework. Second, we have to synthesize a multi-database, develop regional data as model inputs to drive the model. Third, we will integrate model and data to quantitatively investigate the impacts of multiple CSA practice on agro-ecosystem, including agriculture, food, production, greenhouse gas emission, carbon sequestration, and nutrient leaching. Our CSA model is built on the existing agriculture modeling framework. The model has the capability to simulate natural and anthropogenic factors and output the diverse variables. This figure shows you the basic processes regarding the water and biogeochemical cycles. I don't want to go to the details, but just want to show you that the model capability to simulate the multiple stresses and multi-processes at atmosphere, plant, soil, and water interface. Here is the conceptual model of CSA, climate smart agriculture practices. We incorporate no-till, cover crop, and biochar practice. We care about output, crop yield, greenhouse gas emission, nutrient leaching, and water dynamics. This model is built on our existing agro-ecosystem modeling framework. And the table shows you the major inputs. Since I came here, many people always ask me, wait, what's your model inputs? You can see that for such process-based model, we do need a lot of inputs. At a set level, we do need people can help us, identify some initial conditions like planting, date, harvesting, and crop type and management practice. All this information help us to build up initial and boundary conditions. For the regional studies, we will generate database regarding climate, land use by ourselves based on multiple data sources. Model outputs, according to different research objectives, you can see that model can output climate-related variables, crop-related variables. For CSA, to identify CSA if it's effective practice, we need to know the multiple indicators. We need to understand systematically investigate greenhouse gas emission, crop yield, soil organic carbon, and the nutrient leachings. So that's basic model outputs. Over past 4 years, we synthesize database based on published data. You can see we use meta-analysis, collect the data, all published data regarding set-level studies. We also collect set-level observations and develop regional database with different resolution, spatial and temporal resolutions for different research areas. All this data preparation and development help us to build up the conceptual model, help us to calibrate the model, and drive the model for regional simulations. Below, I'm going to introduce several programs closely related to climate smart agriculture programs. The first one is regarding no-till system impacts on agroecosystems at site and regional levels. This program supported by my startup and Hatch proposal. Yawen is my first student. He joined me in 2016 spring semester. His background is atmospheric science. I told him that if you are going to take the responsibility to develop no-till system, the module, you have to systematically understand the interaction of plant, soil, atmosphere interactions. Yaven's smart. And after 2-year training, he got totally understand, the systematically interactions and processes at atmosphere, plant, and soil interface. The first step for him to synthesize data, collect all, publish the data to show how no-till system can help soil sequester carbon, and if it can be used as an effective CSA practice. Our meta-analysis study results show that, yes, no-till system is an effective CSA practice. It can reduce greenhouse gas emissions, particularly for carbon dioxide and methane, and also can increase carbon sequestration. But the average effects on crop yield is not significant. Based on the fully understanding of no-till system on ecosystem, agroecosystem, Yaven developed the conceptual model of no-till system. The system with or without tillage system, tillage treatment, we consider the mixing effects, mulch effects on carbon, water, nutrient processes. When we build the conceptual model, we collaborated with field scientists, John and Hannah, using our almost a half-century long-term no-till system experiment support our study. Levin's long-term no-till system provided us, the no-till system with 4 different nitrogen rates experiments. We pick up 2 with 0 and the highest, with and without nitrogen limitation. In addition to site information, as I mentioned before, we also need to generate other environmental factors like climate change, precipitation, temperature, CO2, and nitrogen deposition. Before we apply the model into long-term simulations, we calibrate and evaluate model simulations by using observed crop yield, soil organic carbon, and soil emission, CO2 emissions. You can see that generally our model performance can catch the general pattern. And particularly for this data set, with Dr. Jacobson's support, we started observations, data collection regarding greenhouse gas emissions. Last year, you may see the large variation and the general pattern from a high to low CO2 emissions. Our further analysis show that large fresh litter contributes large CO2 emission at the beginning. Then with the litter for amount decreased, CO2 emission decreased. We're not quite sure if other factors like soil moisture and soil temperatures, if we have more observations, that are going to be very nice, support model calibration and evaluations. This is the model simulation results over past half century, you can see that since 1970, soil organic carbon under till no-till systems. No-till system slightly increased compared to the first year, serve as a carbon sink. But tillage system slightly decreased. We appreciate Hannah's work. You can see the soil organic carbon measurement last year. Then we isolate the carbon input-output pathways. We try to dig out what caused the carbon sequestration or carbon release. Carbon input, including litter-fall, cover crop biomass, corn residue. And you can see that compared to no-till system, no-till system has higher cover crop biomass input and the corn residue higher than tillage system. Carbon output pathways. Clearly, carbon emissions through soil respiration is a major carbon release pathway. And compared to no-till system, you can see that no-till system has less carbon emission compared to conventional tillage system. So the overall carbon change led to the carbon source and a carbon sink. Not only the carbon pathways, we care about over past half century, how environmental factors like climate change and the tillage treatment, how the relative contributions to carbon changes in soil. So we conducted model sensitivity analysis to isolate the relative contributions of CO2, precipitation, temperature, nitrogen deposition. You can see that atmospheric CO2 and temperature enhanced soil organic carbon. But precipitation in this area reduced soil accumulation. Tillage clearly reduced carbon sink. Because we choose, the system, no nitrogen limitation. So you can see that nitrogen deposition has no significant influence. But we are going to conduct a further analysis regarding, nitrogen limitation system. Then we calibrate our model in other sites. For example, KBS in Michigan area. We calibrate crop yield and N2O emission in soybean and wheat system. Then we apply the model into the United States to test the relative contribution of no-till system compared to conventional tillage system. The map shows the difference between no-till and till system. You can see that the average crop productivity and N2O emission across corn and soybean system different. Generally, we found that compared to conventional tillage system, no-till can slightly enhance crop yield in corn and soybean systems across the United States. But we should be noticed, N2O emission at the same time stimulated by no-till system. So through this project, we found that, okay, we have built our model that has the capability to simulate diverse tillage system. And the site-level studies explore that in Kentucky region, no-till system is more resilient than tillage system. Regional studies explore that when we consider apply the no-till system as a CSA practice at a large scale, we should consider the benefits not only to crop yield, but also consider the environmental consequences like greenhouse gas emissions. Our both site and regional studies show that we do need more observations, not only in Kentucky region site and other sites. We call for more observations regarding soil physical, biological observations, and call for new experiments, like not only one CSA practice. I will talk about that why in the following slides. Derived from this program, we have some products. Yavin published his meta-analysis paper regarding no-till system impacts. And he recently finished the site-level simulations regarding the half-century soil organic carbon responses to no-till system and climate change. We also presented the results in international meetings. Based on the preliminary results, we proposed the idea to NSF RSP program. Luckily, we got the funding support. And then we conducted the further research programs related to CSA. In this program, we expand no-till CSA practice to others, including cover crop and biochar practices. Peter is a minority undergraduate student supported by the program. Visiting student Xiong and my student Yavin also help participate in the program. So we also conduct a meta-analysis, try to explore how cover crop, tillage, no-till, and biochar influence soil environment processes and final influence the soil organic carbon. The results explore that biochar is the most effective CSA practice, can enhance soil organic carbon about 40%, followed by cover crop and no-till system. Actually, conservation tillage, reduce the tillage and no-till system. But through this study, we do find there is none studies at set level, field experiments, conduct all three CSA practices. That's why we call for new experiments. We don't know, maybe those three practices together can enhance more than 50%, or maybe less than 50%. We do need, new field experiments to support results and guide us for future. Through these studies, we also yield one paper regarding the soil organic carbon in response to three widely adopted practices. That just published on Wednesday, online version. I already received more than 6 people asked me about the PDF files. I think that topic already received a lot of attention. And based on the results, I proposed ideas to scale up the impacts of CSA practice from set level to continental large scale. I submitted a proposal to NSF microsystem program. This program kind of, the right home, favors large scale and continental scale modeling work. Next, I'm going to introduce this research program related to CSA practice for water issue. Collaborate with my NASA partner, Alex, and faculty members here, Jimmy and Jinze. We got the funding support from NASA Kentucky to address the agro-ecosystem carbon dynamics and greenhouse gas emissions. The program mainly supports Morgan. Her background, engineering, but Jimmy has more than 10 years research experience in karst landscape. Our model definitely need improve to incorporate such features. Bo, group member, his background is spatial analysis and ecosystem modeling. Help us develop, the regional database. Yanjun, that's my PhD student, joined us last fall. She is a fast learner. Already help us, her background is remote sensing. So both Bo and Yanjun help to develop a regional database to support our study. So I want to explain why we need high resolution data for regional studies. That's because coarse resolution data may lose some important information or even provide wrong information. Look at the figure. 9 kilometer, 1 kilometer, coarse and fine resolution data regarding precipitation in Kentucky region. You can see that with fine resolution data and coarse resolution data, precipitation magnitude change or the pattern even shift. Without accurate climate weather condition information, we cannot accurately estimate how climate change influence Kentucky agricultural productivity and other issues. That's why we need a high resolution database. So why we need an improved model? That's because model always need to be improved for your research objectives. For local and regional studies, we need to incorporate the features. For example, in our Kentucky region, karst landscape is our feature. We have to incorporate such mechanisms into land ecosystem model. Then we can accurately estimate water and nutrient dynamics at land and aquatic interface. We started this program, I think, 2 months ago. You can see that we already have some products. And based on some preliminary results, working with other collaborators, we are going to propose another research idea to Kentucky EPSCoR RID program recently. Teaching programs. Over the past 4 years, I created 2 new courses, Ecosystem Ecology and Ecosystem Dynamic Modeling course. Both courses I taught once. You can see that evaluation results that particularly, under my expectation, particularly for ecosystem modeling. That's my expertise. I have a huge passion to deliver the important information to our students here. Unfortunately, or very interesting, I found that some students gave me very negative feedback. But teaching reviewers, 2 professors gave me very constructive and very positive feedbacks. So I learned from teachers' perspectives and the student needs for my future course teaching. I will change some, course contents and to meet student needs. But I want to see, I still insist something I think very important. For example, students in my class can learn in future what kind of models suitable for your studies. You can identify the suitable model types for your studies. I also co-teach with Dr. Wendrot for undergraduates, climate change and agriculture. I enjoy the teaching and I'm happy to see students' active responses. This course closely related to my research program, climate change, CSA. So recently, I collaborated with people, scientists, experts here and at Murray State University. We found a good opportunity to propose research idea, bring climate smart agriculture education into Kentucky classrooms. Because all of us see the importance of education for young generations. Teaching skills always can be improved. I really appreciate, some faculty members here. Anytime I can step in, ask him, Mark, Dave, Elisa, Olga, they shared, their syllabus and their experience. Chris always encouraged me when he heard about, the ecosystem dynamic modeling course results. I think I learned a lot. And also I participated in training workshops provided by our university and college. I will continue working hard to improving my teaching skills and also adapt the course contents according to student feedbacks in future. In addition to teaching and research progress, I also actively participate in social activities, academic social activities and services to extend my collaborations. I think that can help me to build a new network, expand my collaborations. Because my research background, as I introduced at the beginning, I really care about relationships between agro-ecosystem and the whole environment system. I want to see my success and progress rely on all of your support. My group members, their effort and wisdom make us get research progress. My collaborators provide data support and help generate a new idea for research programs development. Todd always reminded me as an assistant professor, you should create new direction. You should develop research programs with new direction. Yes. That urged me, and with his suggestion, I developed my own network and build up collaborations here. Though I mentioned that people recognize the importance of my research field, over the past several years, I experienced a hard time for funding resources, particularly for global environment and climate change research fields. There are limited funding resources. My mentors help me identify the problem and guide me to seek the suitable agencies, help me successfully get funding support for my career development. I also appreciate my family member, both my colleague and husband, my children, and my parents. My son just turned into 4-year-old last week. So you can imagine, over past 4 years, I experienced mental and physical stresses. But I see a lot of good models here. I learned that's life. All of us play the multiple roles at the same time. And I always see smile fading, Sharon. And all of you always willing to support and help. Anytime, as I mentioned, I step in the office, ask a question regarding teaching and research programs, because you just stop and then talk to me. Right, Mark? So I think I experienced the most difficult time. And now I feel I'm a Kentuckian. There's limited room here. I didn't list, all people here, my collaborators, people who helped me. Just want to see, yes, I need to keep passion and confidence. I have huge, passion on my research field, and I'm looking for promising, opportunities in near future. I think that's all what I want to say today here. I thank all of your attention. And if you have any question or comments, welcome.
Nitrous oxide emissions and no-till versus conventional. That looks like
higher.
Far outweighs like any climate benefits from carbon. I was kind of wondering what is the mechanism for that? Or, do your models point to any ways to reduce those nitrous oxide emissions?
Okay, Jason's question is why no-till system stimulate nitric oxide emissions? What's the mechanisms, right?
Yeah.
That's a really good question. I think we conduct research, through output the model variables, not only carbon, also water and nitrogen-related processes and variables. Yes, we found that maybe that's because no-till system influence the soil, the soil carbon and the soil temperature and the moisture. Both the combination effects stimulate nitrogen oxide. When stimulate and surpass the carbon release, available carbon stimulate available nitrogen. Then nitrogen resources increased, contribute to nitric oxide emissions. We have to do more research and further analysis regarding this. And also, I think that's related to model improvement, because our current model have no such mechanism like, microbial activities, enzyme effects. That's a further work we do need to consider. Maybe for the long-term no-till system, you can see that, yes, we just consider the carbon input through litter for cover crop and corn residue, but how the long-term no-till system change the inner microbial size and enzyme effects, no, that's still a black box. Yeah. Yes, please. Dr. Wagner.
Is it reasonable to just do the modeling with high nitrogen input and low nitrogen input?
Oh, yeah, you're talking about Blevins. You mean the regional study results or for the set level study?
Probably better on a regional level.
Or regional studies.
In other words, if you're asking about, I mean, the nitrous oxide is coming from the fertilizer application.
Oh, yes. Yeah. Because we simulate the, corn system and soybean and corn system across the United States. We consider the nitrogen inputs from 1979 to 2015. Yes, that's the major nitrogen source, stimulate nitric oxide. Yeah.
And if you're asking a question about mechanism, that you could do it with two different levels of nitrogen.
Oh, these simulations, we just compare till no-till system. But for other information, we use historical survey data and the data, develop the data based on the historical records. Yes. But I think you are right. Yeah. Maybe in future we can, as I mentioned, for the set level studies, we can conduct, study not only for the nitrogen fertilizer, no limitation. We should compare, the system with nitrogen limitation systems and the till no-till system. That's important because in future we should consider, the nitrogen inputs. We should enhance nitrogen use efficiency, may reduce the nitrogen inputs. And then in combination with no-till system, how the crop yield, soil organic carbon responds to such system or treatments. Yes. What else? Oh, Todd, please.
So you listed that you served on the NSS panel and the USDA panel. What were those panels, and then what hints would you give me about what makes a quality proposal after you served on those panels?
Okay. Todd's question is, I served as a panelist for USDA or NSF programs. Then my perspectives for the qualified proposal, right? That's a complicated process. First, I think the proposal, at least a panelist, if there are 3 or 4 panelists, there are no people strongly refuse or object, the proposal. That means all of people will feel, yes, the proposal, written in logic way. And research data, research methodology, and the expected outcomes looked reasonable. And the research team is very important, particularly for some collaborative program. For example, I think the USDA, this early year, regarding the collaborative program, how you collaborate with people in computer science, extension, research, education together. So if you lack of one of components, maybe someone exactly question and raise the problem. I mean, exactly following the guideline, the solicitation, and develop your research team, then prepare well, prepare earlier for the writing process. Yeah, I hope I can get a succeeding, national level funding support a lot in future and show people that, yes, I learned a lot from serving as panelist.
Okay, everyone, well, let's give Lee one more hand.
Thank you so much.